Well, welcome to another Fibre Laser Learning Lab. As I promised you last time, we're going to look into one of the, what I would call tricks of this type of laser machine, which is a MOPA fibre laser machine. Now, I'm told that you cannot perform this trick with a Q-switch laser, and certainly can't perform it with a constant wave laser. So we're going to look into the secrets behind this trick, as I will call it, that this machine can perform, to see if we can understand what the mechanism is and whether or not you might be able to do it with a Q-switch laser. Now, I suspect that many people ahead of me have tried to do it on a Q-switch laser or even on a constant power laser like that, but I think you'll get to understand that I don't accept that the round wheel is the best wheel. For instance, a square wheel has got some great properties. You don't need a handbrake in your car, and it discourages theft. So I'm going to go out and explore all the possibilities. Although we want to get to a conclusion on this subject, I'm afraid the conclusion will not be in this or any session soon, because I can foresee that as I start progressing through this, I shall get pulled off into all sorts of different side directions because I need to understand various other features that will go to finish up building the final picture. So let's get started. Now here I've got a piece of very thin stainless steel. It's 0.5 of a millimetre thick, and it's got a nice shiny surface to it. And just here we've got a blow lamp. So I'm going to put the blow lamp behind there. And first of all, you'll see the metal distorting. And then hopefully, if I can control the temperature right, don't get it too close. I want it to happen slowly. Can you see the way the colour is changing on the surface there? I'll now hold it a little bit closer and keep it there. Now you can see, look, we've got it so hot, it's glowing red hot. And if you watch carefully, you'll see that the colours are growing around the outside. I've known about those colours since I was a very, very young engineer, because that was one of the first things they teach you when you're in the training school, how to harden metal, using these colours as what they call tempering colours. Now, these are basically colours of oxide that are formed when you heat metal up, but they're not colours in the sense that you normally see colours. Now, when we look at that red fire extinguisher there, we see it's red because we've got white daylight shining on it. And white light is composed of all the colours of the rainbow. But basically what's happening here is all the colours that are not red are being absorbed by the paint pigment that's on the outside of that container. And it's only the red that's being reflected like a mirror back at us. So we normally see colour by what I would class as subtractive absorption. We only see the colours that are reflected off the surface. We don't see the colours that have been absorbed by the surface of the material. Now these are always nice, clean, crisp, clear colours that we see. So when we look at these colours here, they're nothing like normal absorption colours, because these are created in a completely different way. But you can never get a pure red, a pure blue or a pure green from this method of producing colours. And this is the method that the MOPA laser uses to produce colours. It's this technique here of oxidation on the surface of stainless steel particularly. It can be done, as I understand it, on titanium. I can't prove it on titanium because I don't have any. Now in daylight out here, virtually however I hold this, whichever angle I hold this at, we've got a nice mix of colours. There are no pure colours there. There are just these mixture of interesting colours, sort of mauves and bright teal blue and a golden yellow and a honey colour. Now look, if I twist this, what we're looking at there is an image of daylight from outside, and that's the image from inside under artificial LED light. These are not real colours, these are strange colours that are caused by some very interesting phenomena of light. Now here is a sample test piece given to me by Lotus Laser to show me what the MOPA type laser can do that a Q-switch laser cannot do. Produce all these lovely colours. Look at that lovely green there. And in daylight, hello, where's the green gone? Where have all the colours gone? So, provided we get the light in the right direction, we can have the colours. So here we've got it under our LED light, and if I get the angle of the light right, maybe some of the colours, well, you can just about get the green there, provided I shine the light on it right, I can get the green to show. Otherwise, it's not green at all. Although this is one of the big selling points that they point out to you for a MOPA laser. So first off, let's go and see how these pseudo or false colours are produced. Well, we're going to start off with the electromagnetic spectrum, courtesy of Penn State College of Earth and Mineral Sciences, which is where I found this very nice diagram. Running from cosmic rays at very, very short wavelength through the ultraviolet, then the bit that we can see, and then the infrared where we're working. Normally we work with our 10.6 somewhere here, but now we're working pretty close to the visible spectrum. This is only 750 nanometers, and we are at about 1060. So we're not much further up the scale than the visible red end of the spectrum. But my real point of showing you this drawing is you can see that we've got a visible sensitivity in our eyes between 350 nanometer wavelength light up to 750 nanometer wavelength light, and you can see the way in which the colour spectrum changes. Now, the colours that we've been seeing up to now are really probably not going to be found on this scale because they're not pure colours. Now, you'll recall this image of me heating up the back side of a piece of stainless steel, and here we've overheated it to such an extent that we've made it red hot. You'll notice that the spectrum of colours that we're creating are always on the outside of this area. I mean, it's an indication very much like the energy density in the laser beam. It's probably following some sort of Gaussian distribution where we've got very little heat on the outside here because you've got conductivity of the material, you've got a large radiation area down to air temperature, normal air temperature, and so the heat within this material is very quickly dissipating, and it'll be warm out here but not hot. Now, what sort of temperatures are we talking about here? That's really what we're interested in. What about the red hotness to start with? There's a scale of colour which has been devised, and I would guess that we're not right in the middle there. That possibly could be classed as bright cherry red. Around this area here, it's red to dull red. So possibly we might be up at 800 degrees C in the middle here. Let's see what happens when we take the heat away. Well, the answer is that. So that was the boundary almost of our red hotness. And within that boundary of very high heat, look, when we look at the oxide that's been left behind on the surface, it's this teal blue, going to a darker blue there and then merging to a sort of a mauve and then a brown and then a light straw. Well, there are temperature definitions for each one of these colours. So for instance, the outside edge there, called faint yellow, which is right out here, 176 degrees C. Light straw, which is this secondary phase in here, 205 degrees C. It's only 29 degrees C hotter, but it changes from faint yellow to light straw. And then we've got this area here which is classed as light blue, and then all this section in the middle here is classed as grey blue, and we're talking about 371 degrees C. So let's just put that on the chart there, that somewhere around about there, 371 degrees. It's rather interesting because look, we've heated that all the way up to 800 degrees C and 500 degrees C in the middle there. As it cools down to 371 degrees C, it creates this colour. So, but the thing I want to emphasise here is we've created these colours with a blow lamp, a very crude instrument. But it does require these temperatures here, up to 371 degrees C, to produce these colours. Now, as I explained to you in the previous session, temperature is only a function of the vibrational level of the material. So 371 is not very hot. The question is, how do we control it? How do we make it happen? Do we need long pulses? I mean, it takes a lot of energy to put that much into the surface. Now, we might not be able to see any accurate colours on here, but what we can see is that we've got very accurate control of the shapes. So we haven't got a lot of overheating and heat flow away from our marking area. Now, in the previous session, we talked about this material, which is aluminium. And if you remember, I said to you, oxygen and metal will automatically form an oxide layer on the surface. It's incredibly thin and it's completely transparent, as you can see here, because this looks like raw aluminium. But I know that it's not, that there is an oxide layer on that surface there. Now, this shiny surface on the stainless steel is even more sensitive to the advances of oxygen. Let's just have a quick look and I'll explain why. Stainless steel has got a very high chromium content, 18 to 20%. Oxygen and chromium are absolutely in love with each other. So this has got a very thin layer of oxide on the surface. It's much thicker than the aluminium. It's probably something in the region of about 2 nanometers thick. I don't know what that is, maybe 6, 8, 10 atoms thick. And literally, as soon as you damage the surface, within a few nanoseconds, so I'm told, it will heal itself, which is why this material is stainless. It's self-healing and it's continuously protecting the surface with this chromium oxide. This very thin layer of chrome oxide on the surface, as you can see, it is transparent because we can see through to the shiny material underneath. And that leads us to a phenomenon that you have seen many times before. I give you the soap bubble or an oil film on a puddle. Yeah, I think this is a very interesting composite picture that's not real, because if you take a look here, we've got these 3 trees here and we've got these 3 trees here which are one and the same, and they've just rotated the image to give you a nice general impression. But what you have got here is all the typical colours that we're seeing in here. But these have had no heat in them at all. So where do those colours come from? Now, you might want to go and do your own research on this, but I'm very quickly going to go through the thin film interference theory, which is what we're talking about. It's a phenomenon associated with light and light waves. Very, very crudely, we have a light wave that comes in and strikes the surface of the film that's on the top there. And then we've got a certain film thickness here. Let's call it T. I'm not going to get too technical about this. You can go and do your own reading on this subject, thin film interference. But generally, not always, but generally, there is something called a phase reversal as the light hits the surface. So it comes on, for example, let's just call these +1. 0 is obviously these point here, and -1. So we've got a complete mirror image of what came in. So that's the first thing that happens. We get this light coming in and reflected off the surface. And then we've got this thin film here. And as we can see through that thin film to the material underneath. So the light travels into that thin film. Okay, so it's only 1 or 2 nanometers thick. But that means the light is traveling further. The color remains the same, but the speed of the light actually slows down. And as it slows down, so it changes its angle. And instead of coming through and hitting the bottom just here, as you might expect, it hits the bottom here. And then it bounces off the bottom, again, probably with a phase reversal, comes out at the same angle as the reflection. These light beams are no longer in phase. Look, the top of this one is now no longer in line with the top of that one. So the colour that came in and the colour that came out will be the same, but it might not be as intense. So you can get something called additive or destructive interference between these two beams. Now, I've drawn them a long way apart. They're not going to be a long way apart. So the simple story that I want to get over to you here is we send one wave in and we get 2 waves out, one off the top surface and one off the bottom surface, and those waves interfere with each other. And I'm now going to show you the effect of those 2 waves interfering with each other.
Now, I'm indebted to the guys that created this piece of software because it makes my life a lot easier in trying to explain light waves to you. Now, waves are waves, whether they're light or sound, they all look the same. So what we should be doing is hearing colour rather than seeing colour in this demonstration. Now, the annoying buzz in the background is a colour, because this is what a colour looks like. Now, the only difference between colours is this: the length of the waves. Now, that's the red long wavelength frequency. There's one wave on the screen, that's a long wave. Now, if we double its frequency and we put 2 waves on the screen, that's a different colour. But you can hear it's a different colour. But you can hear that it's a lovely smooth colour. Now, that relates to all those colours that you see on the colour chart, the colour range that our eyes can see. Every pure colour has got this lovely sine wave shape to it. Now, when we get 2 different coloured lights mixing together like this, they produce a single wave which is completely different. It's the sum of all these bits and pieces here. So if we look here, we're going to get addition of the red and the blue, and here we're going to get subtraction of the red from the blue. So we're going to get a rather strange waveform, and if we use this little slider here, it'll show us what happens when we mix the 2 together. Now, in the thin film picture, I showed you that the first wave came out, let's call it the blue wave, and then the second wave came out at a different point and a different phase. So there was a shift between the 2 waves, and that shift basically is going to cause an interference pattern between the 2. Now, it's not going to cause a colour interference because they're both the same colour. What it's actually going to do, if we listen very carefully, at that point there, they are 180 degrees out of phase. The pluses of one wave cancel the minuses of another wave, and the net result, as we move on this slider and have a look, is 0. So we have no colour at all now. We've got blackness. So the phase shift, and this is called destructive interference, actually cancels the light out. And as we get further and further into phase, we get back to the original intensity of light. So we've got phase shift to think about, and we've got this mixing of different types of waves. Now, there's a further mixing effect which takes place, and that's when we get several colours. Now, when we start changing the frequency of these, let's see what they net out as. See, that's a really weird signal. And that's the sort of light, you can hear that it's not a pure tone, and you can see that it's not a pure sine wave. It's some strange waveform which gives these weird colours that we're talking about. It's an interference effect. And that interference effect changes as the thickness of the film changes, because as the film thickness changes, so the relationship between the wave going in and the wave coming out changes. But of course, we're not just talking about a single colour wave, but much more complex than that. We've got thousands of light waves of different frequencies entering and thousands of light waves of different frequencies exiting. So we get a massive combination of all these frequencies and colours that are interplaying with each other. Hence these very strange, non-standard colours, as I will call them. They're not colours that you're likely to find in the standard colour chart.
When you look at that straight on now, everything looks pretty dull and black. But if I move the camera and move this into the light, so you're still looking at it straight on, at a certain angle of incidence of light, the colours appear. So you're still looking at it straight on, but the light angle into the surface has changed. So we've got light coming in here, and we've got your eye there, and depending on the relative difference between these two angles depends on the colour that you see, because it depends on the distance of T, the thickness of the film, and the lower the angle, the longer the distance, the more the interference between the two. So all of these little black patches and black things here, when you catch them in the light right, you can make them either disappear or turn into pale grey. Now, I suspect that some of these have been done with scans across this way, and some of them have been done with scans across that way, so that depending on how the light catches them, maybe they do or they don't disappear. So to sum up, none of these colours on here are pigment colours. They're all refraction colours caused by this thin film interference effect. Yes, we used a lot of heat to create these colours, but we didn't use any heat there. We have to draw the conclusion that the only thing that the heat is doing is changing the thickness of this film. So I'm afraid there is no magic pen that this machine has which paints different colours on the surface of stainless steel. It doesn't even require heat to produce these colours. It needs a thin, transparent film. We're going to have to manipulate the thickness of this film to produce these non-pigment colours. But when we come to modifying the film thickness of stainless steel, here it appears that we need to have certain temperatures to create these colours. I'm not sure that we have to locally heat up to these temperatures to produce these colours. It could well be that if we stimulate the surface, we might be able to promote growth in stages. Sometimes you can't crack the problem with logic. And in this particular instance, I felt, hey, it's very simple. If we fire the MOPA laser at this surface here, the MOPA has got the ability to dispense very, very small, precise amounts of light energy. And that light energy will be stimulating the molecules in here to higher and higher temperatures. And those higher temperatures, just local temperatures in this area here, are going to, if you like, percolate out into the background material and heat the background material up by conduction, okay, before it dissipates away to nothing. But having heated the background material up, that's an improved environment for the combination of oxygen and chromium, because adding heat to any chemical reaction speeds it up. But hey, the film is chromium oxide, so it's already got its oxygen. So I'm a little bit puzzled as to whether or not we're going to be able to promote growth onto the surface of the thickness, or whether we're going to be trying to promote growth into the material. maybe just heating this little area up throws everything into confusion and we can actually get below the film. I say maybe. I told you before, I'm not a chemist and I'm not a physicist, so I don't understand exactly how this mechanism works. But what I do know is we're going to have to change the film thickness to change the interference patterns between the incoming and the outgoing light. So in the next session, we're going to get dragged off onto one of these tangents that I mentioned earlier. And we're going to have to investigate the actual power of pulses that we have on this machine. We're going to have to look at ways in which we might be able to find a strategy for thickening this film. I could go and ask Lotus Laser, but I'm not going to. So on that stubborn note, I'll say cheerio to you and we'll catch up in the next session.